Hello guys, so in this video I will be covering a very important topic of class 11th chemistry from the chapter structure of atom. The whole chapter is very important, but this topic is also, I think, one of the most important topics of this chapter, and a lot of questions are asked on this topic in JEE, NEET, CBSE and all sorts of exams. Alright, so let's begin without any delay. I have already listed the topics that I'll be covering in this lesson, in this video, in this order. You can tell me what other important topics you want me to cover down in the comments, and I will be sure. And after watching the whole video, if you have any doubts remaining or if you have any questions that you want me to solve, I will definitely do that. So you can just drop it all down in the comments. I will be responding to every comment I get. Alright, so I will try to explain this topic in a manner such that you can do any question of any exam after watching this one video. Alright, on this particular topic obviously, and after some practice. So the topics that I'll be covering, which are already listed, is I'll be starting with the Schrodinger wave equation, because this is what the whole topic is based on. Alright, then I'll be moving to quantum numbers, and after you learn about quantum numbers, I will teach you how to write the electronic configurations and the rules that are based, and there's some important rules that there are on which the electronic configuration rules are based on. Alright, and then I'll move towards what nodes are, what they mean, and how to calculate the number of nodes, because direct questions are asked in competitive and CBSE exams. And I will be then discussing some hand-picked important questions and PYQs related to this topic. Alright, so make sure you watch it till the end. And so we'll start with Schrodinger wave equation. So I have written the equation down here, right? This is the whole equation. Now this seems very complex, but if you want to memorize it, because I remember in a PYQ, this equation was asked directly in a PYQ or in a question I when practicing. This equation was asked directly. So this equation is not too hard to learn. It is d square psi by dx square, d square psi by dy square, d square psi by dz square. This is like very simple, and then you just need to learn this thing. Alright, this thing you need to memorize, which is not that difficult. Alright, then we have this potential energy. V is potential energy, m is mass of electron, x, y, z are coordinate axis, and E is total energy. Wait, I forgot to mention one thing here, that this symbol is called psi. Alright, this symbol is called psi. I forgot to mention here. Alright, and this is obviously called psi square then. Alright, so now what does all this mean? This is basically a wave equation. We get a graph something like this, or we will be discussing graphs of some particular orbitals. Alright, we will be discussing the graphs of some particular orbitals or subshells, right? Towards the after I teach you how to write the electronic configuration. Alright, because only, and teach you about nodes, because only then will you be able to understand it properly and understand what tricks I will be telling you. Alright, now this equation is basically, we can also rewrite this as Hamiltonian operator psi equal to E psi. Now I know this does not make much sense, but you just need to memorize it, because all of this is not in our syllabus. Alright, this is something beyond our syllabus, so we do not really need to know more about this operator. Alright, so this is psi is the amplitude. Alright, like this is the wave equation, right? So the amplitude, this is denoted by psi, and the psi square. Alright, so basically what happens is, where we write the wave equation, and where the probability of finding the electron is maximum, yani ki the amplitudes, right? The amplitudes, that means that there is the maximum probability of finding the electron. So the psi square denotes the probability density of the electron, of finding the electron, like what will be the probability that we'll find the electron here, right? And psi square can never be negative. If you see, psi square can never be negative, can never be negative. I forgot what's that. Right, it can never be negative, and that makes sense as well, because it is the probability, right? And you cannot say that at a place the probability of finding an electron is minus 0.5, because that does not make any sense. Probability, negative probability does not make any sense. So that is why psi square will always be positive, and that also makes sense. So I hope this whole thing makes sense to you. This is all you need to know in the Schrodinger wave equation, and you will find the use of this. I will explain it in a very clear and helpful manner that will always help you keep all this in your mind at all times in the next session of this video. So we are done with the Schrodinger wave equation. Now when we move towards quantum numbers, you will understand the significance of this wave equation and the significance of this psi. Otherwise we will not be we wouldn't have been studying it if it was not significant. But as I said, the whole model is based, the whole quantum model is based on this one Schrodinger wave equation. So it is a very important equation. Alright, this psi thing is very important, as you will understand as we move through with the video. Alright, so before we go into detail of quantum numbers, I would first like to give you an idea on what exactly quantum numbers are, and why do we use them, and what is the purpose of the whole wave equation that we learned, and the relation to the theory, right? Alright, so this wave equation, you see this wave equation, this psi symbol, this determines three of our quantum numbers, which is the principal quantum number, azimuthal quantum number, and magnetic quantum number. And the spin quantum number is something else. Spin quantum number is something else, but it is also a quantum number, but it is not determined by psi. Alright, this might be asked, so I'm just telling you that this. Alright, now why did I write the address of Sherlock Holmes here, right? Why did I write the address of Sherlock Holmes? The Sherlock Holmes fan will get that, but those who do not watch Sherlock Holmes, I'm just using this address as an example. Alright, so basically through the quantum numbers, we can give the address of the electron. What I mean to say is that we know that this is an electron of sodium, right? We know that. Now where can we exactly find it, right? For that, what do we need to do is we need to use this wave equation. Alright, after using the wave equation, what did we find, right? What did we find? Now we write the position of an electron like we write an address. I just wrote this address to make it very clear that we just write the address of the electron like we write any other address. For example, first I will give you an example of an electron. I'll just write here. Let us assume that we are understanding 1s. Alright, 1s. Okay, so basically what we need to understand is that our principal quantum number gives us the shell, azimuthal quantum number gives us the subshell, and magnetic quantum number gives us the orbital, and in the orbital resides the electron. Alright, 1s has this orbital in which the electron will reside. Alright, this is what I mean to say. Now, like for example, first we know that the electron is of sodium. So if we know the electron is of sodium, similarly we know that there is a person residing in United Kingdom. We know that Sherlock Holmes lives in United Kingdom. Alright, similarly we know that the electron is in sodium, but that does not do us any favors because we do not know where in United Kingdom or where in the atom, because they are both so big, right? Now we get to know from the principal quantum number the country, like the state, sorry, not the country. From the principal quantum number we narrow it down to a orbit. We narrow it down to a orbit or a shell. They are both the same things. Orbit or a shell is the same things. We narrow it down to a shell or orbit, like they are circular in nature around the nucleus. Alright, we narrow it down that you will find it somewhere here. So for example, you will find it somewhere in London, but still London is also so big, we do not know exactly where, right? Now we know that you will find it, I can narrow it down further and say that you will find it in the S subshell. Alright, like the first orbit you will find it in the S subshell or Baker Street, right? Like we are narrowing it down. Are you getting my point? I just want to explain that how slowly we are narrowing it down. Okay, then we have the house number, which in this analogy I am going to take as the orbital, which will we will get the kind of like the exact position where the electron will be. We get an area where the electron might be residing. Alright, but now also in the orbital also we the spin quantum number gives us the orientation in which the electron is placed. Like we know the electrons are always spinning, so it has the anti-clockwise spin or the clockwise spin. Alright, the spin quantum number only gives us that, right? I hope I am clear. I hope that I did not confuse this too much. Basically, what do you need to understand, that quantum number gives the address of an electron. That is what I was trying to make clear here. Alright, so if we are clear with the introduction, we will go forward with understanding each of these quantum numbers separately and what use do we have of them. Okay, so the first quantum number that we need to learn about is the principal quantum number. Alright, the principal quantum number. Now I have wrote all the important points that I think are necessary that you need to learn in the principal quantum number. It basically tells you the size of an atom, because the number of shells are in or orbits, they are exactly the same thing, do not confuse them. The number of shells or orbits in an atom, the more will be the size, right? It's right, they are circular in shape. It's based on Bohr's model. I am going to assume that you already know about the Bohr's model, you have enough knowledge about it. Because in the Bohr's model it only says that the energy of an orbit is fixed, then it gains energy and then it comes back, like all that, right? So Bohr's model, it is based on the Bohr's model. Principal quantum number, it's circular in shape, energy is fixed, it is denoted by KLMN or 1 2 3 4, and the number of electrons, I forgot to write here, the number of electrons in a subshell, in a shell is 2n square, right? In a 2 it's 2n square, n being the principal quantum number. And it also tells us about the energy of an electron. This is also from, I think, some previous thing that we had studied, but still I wrote it here again, that it is E energy is 2 pi square m E4 z square by n square h square. H is the Planck's constant, n is the principal quantum number, z is the atomic number, E is the electronic charge, m is the mass. And I wrote it in 3 different units that can be asked. वैसे तो it's given in the paper that whatever unit it is asked, the hydrogen one is given, from that it's like 1 1, right? So from that you can find out, but still in case it is not given somewhere, you can it does not hurt to memorize it if you can. Obviously this EV1 is the most common one, just saying for the sake of it. Alright, so now let's move on to the next quantum number. Azimuthal quantum number. It is also known as the subsidiary or angular quantum number. Alright, it denotes the number of subshells in a shell. It also denotes the orbital angular momentum of an electron, which is given by the formula root of L plus 1 h by 2 pi. L is this obviously, and h by 2 pi is denoted by this symbol. Alright, like a little h and a cut on the top of it, right? And the formula used, right, azimuthal quantum number, how do we write it? We have a formula for that, that if we have a shell, then the subshell would be this. Now you're saying, like, basically it starts with 0. 0 is called S, 1 is called P, SPDF, right? 2 is called D, and 3 is called F. It's just the way it is named. It does not, I don't think it has a very logical reason behind it. And the shell K is also 1, L is also 2, M is also 3, N is also 4. So basically the first shell will have only one subshell, the second shell will have two subshells, and the third will have 3, and similarly so on. Now the number of electrons that can be filled in each subshell, that we will study right now, after that you will understand after we study the magnetic quantum number as well. But for now you just need to understand that for K we for 1 it has the formula 0 to n minus 1. Basically there is a question that is sometimes asked, that can 2D exist? Can 2D exist, right? Now what would you call the answer of this? No, 2D cannot exist, because the formula used for the D, for the azimuthal quantum number, should be 0 to n minus 1, but D itself is 2, right? Here we can see D itself is 2, so 2D cannot exist, right? Okay, so we move forward to the next quantum number. The next quantum number is magnetic quantum number. The magnetic quantum number basically tells the number of orbitals in a subshell. The formula for this is minus L to L including 0. And why it is called the magnetic quantum number? It is denoted by M. So why it is called the magnetic quantum number? It is called the magnetic quantum number because it gives a magnetic moment, which will basically tell you the amount of magnetic field it can produce. The magnetic moment thing you will learn in physics, I think in 12th, so you do not need to go. Okay, the unit for this is Bohr magneton, BM, right? Bohr magneton. This is also Bohr magneton. I did not write it here, but that is the same thing. I think it's understood. This is based on the number of unpaired electrons, and the number of unpaired electrons will come kind of from the magnetic quantum number. Alright, root of n plus 2, and root of 4s s plus 1, and s is n by 2, like half the number of unpaired electrons. So I think it's very easy, it's not that hard. Alright, now the formula, right? The formula, let me explain you the formula. Like for the subshell S, this is S subshell, right? This is P and this is D. This will have 0. This will have only one orbital, that is 0. This will have 3 orbitals, minus 1, 0, 1. This will have 5 orbitals, minus 2, minus 1, 0 and 1, 0, 1 and 2. Alright, here I needed to explain you something. The thing that I need to explain you, that each orbital, this you need to remember always, that each orbital will have 2 electrons. Alright, like it can have one also, but it will have 2 electrons. It has the capacity to contain 2 electrons. Alright, so like for the S subshell, let's say for the S subshell we have only one orbital, so it can have 2 electrons. For the L subshell, it has, we can see here, this is S P D, sorry, not for the L, for the P subshell, it will have 3 orbitals, as we can see from here, right? 3 orbitals. So it can have at max 1 2 3 4 5 6 electrons. For the D, we have 5, right? D subshell, we have 5 orbitals, which means it can at max contain 1 2 3, I'm sorry, this is not very even, but let's assume that this is, all right, 1 2 3 4 5 6 7 8 9 10, right? So it is as simple as that. All right, now we need to figure out some patterns. All right, we need to figure out some patterns. For example, when I said that for a orbit, for, because I do not want you to memorize the formulas for how many orbitals are going to be there, how many electrons are going to be there, I want you to have it with explanation. All right, so we said that in a particular orbit or a particular shell, we will have 2 n square electrons, right? We will have 2 n square electrons, which how can we say that? How can we say that? For this is very simple. For example, if you see the orbit 1, for the first orbit, you will have 0, only 0 subshell, which means you will have only 1 orbital, right? Only 1 orbital. For the second orbit, we will have 0 and 1, 2 subshells, which will give you 1 plus 3, right? Now for the 3, you will have 0 1 2, which will give you 1 plus 3 plus 5, and so on. So if you can see, if you are observing the pattern, you can observe this pattern that for 1 you have 1, for 2 you have the first 2 odd numbers, for 3 you have the first 3 odd numbers, and so on. For 4 you will have first 4 odd numbers, for 5 you will have first 5 odd numbers, and so on. And I think in 6th or 7th class maths we learned that the sum of first n odd numbers is going to be n square, right? So if we have for the sum of first n odd numbers is n square, which means that we will have n square number of orbitals. Are you getting my point? Are you following me? Sum of first n odd numbers is equal to n square, which means that n square are the number of orbitals that will be present, and in each orbital we can have at max in each orbital the capacity of electrons is 2, right? So for n square electrons, the capacity of electrons will be 2n square. There, we proved it, right? For example, so for similarly for subshells you can also do. For subshells, you can first find out the pattern that is going on, which way you will find that the number of orbitals that you will find is going to be 2l plus 1, and obviously if the number of orbitals is 2l plus 1, then the number of electrons you will get are 2l plus 1. I hope this concept is very clear to you. Till right now everything is going to be crystal cleared to you, right? I hope this is what's going on. Now the next topic we are going to move towards, that I want to clarify once. Let's first take, we have this simple topic before I wanted to tell you about the shape of the electrons, but I think first we should cover the spin quantum number. All right, the spin quantum number that we had, right? The spin quantum number is of two types, plus half and minus half, right? Plus half and minus half. One is the clockwise spin and one is the anti-clockwise spin. So the spin quantum number is of two types, and that does not matter because you see now, then whenever I'm putting the electron in an orbital, I have done this pretty many of times. I put an electron like, I put two electrons like this. Why do I put one as this and one as this, like one upright and one downright? I do this because to demonstrate that they have opposite spins. One has plus half and one has minus half. Alright, so I hope this is. Next we move on to the shape of the orbitals. Alright, so for the s orbital we have the simple spherical shape. We cannot obviously elaborate in spherical shape, there is only one kind of spherical, right? Then in p orbital we have dumbbell shape, and in the dumbbell shape we have, like, simple to understand. For px we have the dumbbell on the x axis, for py we have the dumbbell on the y axis, and for pz we have the dumbbell on the z axis. So it's easy to understand, right? Now for the d orbital, which is the double dumbbell shape except for dz square. So except dz square, baki four that we have here, we have dxy, dyz and dxz are very simple to understand. That in dxy we have it in only the xy plane, for dyz we have only in the yz plane, and for dxz we have only in the xz plane, and for dx square minus y square we have only on the x axis and y axis. Alright, now for the donut dz square, it is not double dumbbell. So what it is known as the donut shape, because if you see, you find a little donut. I was feeling I am not able to make it that properly, so I got this image from the internet. You can clearly see the donut around here. Alright, it is around this xy plane and it's around the z. That is why it's called the dz square, because the main thing is around the z axis. Alright, you can memorize it like this. Then f orbital we have a complex shape, like it is so complex that we haven't been able to really understand what it is. So this is all about the shape of the orbitals, and now we will finally move on to, like, we have finally completed another to do in this, which I put is the quantum numbers. We have completed the quantum numbers. Now we will move on to another very big topic, which is how to write electronic configuration. Then we'll move on to nodes, which is a relatively small topic, and then questions related to the whole whatever we learned in the video. Now we move on to the next part of the video, which is going to be about how to write the electronic configuration as we discussed above. So before I teach you how to write the electronic configuration, I am going to show you a little bit about, I'll tell you a little bit about some important rules that you need to know, and then I'll take an example to tell you how are we going to write it, and then some exceptions and some rules. Alright, so let's move forward with that. Alright, so there's some important rules. The first rule that is very important is the Aufbau principle, and it will basically tell you how to write the electronic configuration. Alright, so we know that the Aufbau rules say that electrons are filled in increasing order of their energy, which means that first the lowest energy orbital will be filled, then the orbital that is of more energy than that, and that then that. Like, I think the statement is very clear in itself. And Aufbau, I just wrote it as a side information. It does not really have any relevance, but for side information you can know that Aufbau is the German word for building up. So This is a side information. Now how do we find out that what is the order of energy? For finding out what is the order of the energy, we have this N plus L rule. What is the N plus L rule? It says that the lower the value of N plus L, the lower is the energy going to be, and the higher the value of N plus L, the higher the energy is going to be. And if N plus L value is same, for example in 4s, the N plus L value is 4 plus 0, right? And in 3D, N plus L value is going to be 3 plus 1, no, 3 plus 2, wait 1 second, I confused this, yeah, sorry, 3p and 4s, 4 plus 0 and 3 plus 1, they are both going to be equal to 4, which means the N plus L is same. Then the energy is lower whose N is lower. So N is lower of 3p, so the energy of 3p will be lower than 4s. So this is the rule which we use to find out. And also there is a way, if we write it as 1, 2, 3, 4, 5, and you write S, 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 as S is possible with each orbit, right? But P starts with 2, alright? So what are we going to do is that this row is going to be for 1, this row is going to be for 2, this for 3, this for 4, this for 5, like that. So we know that with 1 only S is possible, with 2 S is possible and 2 P is possible, then 3 S is possible, 3 P is possible, 3 D is possible, 4 S is possible, 4 P is possible, 4 D is possible, 4 F is possible, 5 S is possible, 5 P is possible, 5 D is possible, 5 F is possible, then 5G is possible, and so on. So like that we write this, and then we start filling it diagonally. Like I have made the arrows diagonally, right? Like first it will go like 1s, then diagonally into 2s, then diagonally into 2p 3s, then diagonally into 3p 4s, then diagonally into like that, like this, and like this. Like it obviously this is 6s, so before going into 4f it will go into 6s. So when you expand, like for example if you're going through this, then you try to write the whole. Don't miss that, alright? Don't do this mistake, because this is not the only thing. I've just written a small part of it. This is going to infinitely expand, alright? So I think this is going to be pretty clear to you. Achha, now that we've studied this, I will first tell you how to write the electronic configuration. For example, we have N equal to S, right? We have N equal to S. So first of all, we have, like I will write here, 1s, 2s, 2p, 3s, 3p, 3d, 4s, right? Like this we have. Now the atomic number of N is 7, alright? So first the 2 electrons will go into S, right? So 1s2. Then the 2 orbitals will go into 2s2. Then this will go into, then how many electrons are remaining? We had 7. 4 electrons have already been taken place, so we have only 3 electrons left. Now that the 3 electrons are left, that will go into 2p, sorry, 1s, 2s, 2p, alright? So it will go into 2p, which is 2p3. So this is why, this is how we are going to write the electronic configuration of N. And now you can try on your own writing the electronic configuration of some other elements on your own and then check it out, alright? Or you can ask me if you have any doubt in other electronic configurations. But after watching this whole video, because you are going to miss out on some important points if you don't. Alright, so now there is another very important rule, which is Hund's rule of maximum multiplicity. Okay, so Hund's rule of maximum multiplicity says that pairing of electron cannot take place until each orbital contains one electron, which means that the pairing of electron that in a particular orbital, in a particular subshell, like we have 2p subshell, we have 3 orbitals, we write it like this as we discussed earlier in this video only, alright? So when you have to write 2p3, you will not fill it like first in the first orbital you filled in the first orbital you filled 2, and then in the second orbital you filled 1. This is the wrong way. What you have to do, you have to first fill 1 in each of them. Okay, you have to first fill 1 in each of them, like you filled 1, 1, 1, right? and then if there is another remaining, then pairing will start. For example, for 4d7, we take another example, 4d7. So here you see, you have, you cannot fill it this way. You cannot fill it this way, that you first filled in the first orbital, then the second, then the third, then whatever remains like this. No, this is the wrong way. You do not do like that. You have, like, you have written 4d7. First you'll fill 1 2 3 4 5. You filled the 5, and then now we have 2 remaining, but each orbital can contain at max 2, right? So you're not going to move to the next subshell, but you're going to fill here. Now now you'll start pairing it. So 1 and 2. All right. Now why is this so? What is the purpose of this? All right. The explanation of this, that there is a rule that the spin multiplicity should be maximum. Spin multiplicity should be maximum, due to which exchange energy remains maximum. All right. But what is the spin multiplicity? What is this? So I have written this here. So spin multiplicity is 2 mod of s plus 1. This is its formula. This is what spin multiplicity is called. S is the spin, it's plus half or minus half or 0, right? We can, when it is not given, see, when the electrons are paired up, then you can say that one will be plus half and the second will be minus half, and then you can cancel them out. But when there is given like either this or this, you cannot say it is plus half or it is minus half. You have to just imagine, like, you can take any one, answer will be same because you have put mod over here, right? All right. So when you split multiplicity for, let's for C for 2p3, in which the split multiplicity will be maximum. If we fill, there is one more thing. If you say, this is also wrong. If you say ki you will fill like this, then this one like this, then this one like this. No. First, the same spin needs to be filled and then pairing needs to be started. Okay? So, like you have this. If you fill 2p3 like this, what will happen is, this and this will cancel each other, or this and this will cancel each other. 2 will cancel each other. Alright, 2 will cancel each other. So the effective is going to remain only half. Only 1 will remain effective. So it will be 2 half plus 1, which will give you 2. Alright, let's write this down. We don't know if this is right or this is wrong. Now this, in this also pairing has been done. This will cancel each other. Only this will be counted. So half. Alright. Now, if you write this or if you write this, you will get 2 into 3 by 2, because they are not cancelling each other out. They are going to be add up. Whether it is negative spin or it is positive spin, they are going to be add up and they are going to be mod in the end. So it does not really matter if you take plus half or minus half. So it will be what, 3 by 2 plus half plus 1, 2. So it will be 4. So the spin multiplicity is going to be maximum in this case or this case. These are actually the same case, because first we filled of the same spin, then we fill of the second spin. Alright, so I hope this is clear to you. Okay. Now we come on to another very important rule, which is called the Pauli's exclusion principle. Pauli's exclusion principle can be written in 2 ways. It has 2 definitions. The first definition is, an atomic orbital can accommodate a maximum of 2 electrons, and that must be of opposite spin. This, right? It can accommodate of only 2 electrons, and the 2 electrons should be of the opposite spin. Okay? But it does not feel like an exclusion, right? Why is this name Pauli's exclusion principle? For that, you will get the answer by the second definition. The second definition says, no 2 electrons in an atom has the same set of 4 quantum numbers. How are these two same? These two are same. If you see in this, if in this, these 2 electrons, let's consider these 2 electrons. It has n same, n is 1. It has L same, L is 0. And it has M same, L is 0. Now what is different? The difference is in the spin quantum number. One is going to be plus half and one is going to be minus half. And that is the important thing of it, must be of opposite sign. Though these both are dependent on each other. Alright. So we write it like this. You can write, I just give you for example, like in the Hund's rule, you can write it as this. 1s2, 2s2, 2p3. Alright. Now, as I told you, you can try writing some of the electronic configurations on your own. I will recommend that you at least practice and write the electronic configuration of the first 20 elements to really grasp on how to write electronic configurations and to gain a little bit of speed. Otherwise, you will be very slow and time is a very huge matter. Alright, so there are some important exceptions. Like, I will motivate you to figure it out on your own, but I will still tell you कि there are two exceptions. These two exceptions are like really important and you always need to remember them. Alright, so the first exception is of chromium. It has atomic number 24, but चलो इधर तक it is till here it is very normal, but here you see that 4s2 and then 3d4. In general case it should have been this, but we have done it as 4s1 and 3d5. And copper, here 4s1 and 3d10 has been written. So why? What is happening? The explanation for this is that half-filled or full-filled orbitals are highly stable. Alright, so here we see if you had written 4s2 and 3d4, then this would have been full-filled, but this wouldn't have been half-filled. And if you see, these have very negligible energy difference between them. Alright, so if it gives one electron to it, it gets 4s1 and 3d5. Now both are half filled, right? Because it has one orbital and it will get 1. This has one orbit 5. It will be like it has maximum capacity of 10. Now it will get 5. So it is both are half filled. So this will be much more stable. Similarly in Cu also, it would have been 4s2 3d9, but that wouldn't have done anyone any favors, because this is going to be obviously the better one because this is fulfilled. Alright, now there are some important terms that you need to know. The penultimate shell, anti-penultimate shell, degenerate orbitals, paramagnetic species and diamagnetic species. Now what it is? The penultimate shell. Penultimate shell is the second last shell or the shell before the valence shell. For example in copper, what is the valence shell? Valence shell will be 4. Don't confuse this, because we are putting the electron is going in 3d10 last, but still 4s1 is going to be the last shell that the electron goes into. So this is going to be the valence shell. So the penultimate shell is going to be 3 and the valence shell is going to be 2, because valence shell is the third last or the shell before the penultimate shell. Alright, the degenerate orbitals. Orbitals having same energy, or orbitals having same energy. Here we have an important point of hydrogen, exception of we have an important point of hydrogen. I will just explain it, and here I am just going to write important point of hydrogen. What is the important point of hydrogen? That in normal cases you can see that the three orbitals of this third shell are not degenerate. They all have different energies. But in hydrogen, as there is only one electron, these three subshells are going to be degenerate. Alright, all these orbitals are going to be degenerate. Okay, in the same shell, all the orbitals of all subshells are going to be of the same energy, and that is why they are going to be degenerate. This is an important point. Okay, now paramagnetic species and diamagnetic species. Paramagnetic species is the species in which even one unpaired electron exists. That is paramagnetic species. So in the paramagnetic species, like this is a paramagnetic, this is a paramagnetic, this is paramagnetic, as these are unpaired electrons. But for example, what is not paramagnetic? If you see copper, after copper the element that comes is zinc. When you take zinc, 4s2 it will become, and then we will have no unpaired electron, and that is why that would be diamagnetic species. Alright, now I think there needs to be an important point that you need to learn. One more thing, that if I tell you to write the electronic configuration of Cr plus, if I tell you to write the electronic configuration of Cr plus, then you are not going to take out one electron from here. It will not be 3d4 4s1. Instead, it is going to be this whole as the same. this whole as the same, alright, and then it is going to be 3d5, 4s1, alright. So if when you take out the electron is going to be taken out from the valence shell, whether it is irrelevant, regardless of whether it is the last shell in which the electron is going or not, the electron is always going to be taken out from the valence shell, alright. And also in these cases like these, when you have the end like this, then you tend to write it as 3d5 and 4s1, again regardless of wherever the electron is going last. This is just the way of writing. So I think I covered it pretty well. If you have any doubts, you can ask me. You need to practice writing at least first 20 elements electronic configuration to really grasp the topic. And if you have any doubts, you can always comment down below. Alright, so how to write electronic configuration, we have covered this. Now towards the next part of the topic is going to be nodes. Okay, so what are nodes? Nodes are basically nothing but the areas where the probability of finding electron is going to be 0. Alright, so the number of nodes, how we calculate that? The nodes are of two types. Okay, the nodes are of two types. One is the spherical or the radial node, and one is the angular node. Alright, the number of angular nodes is going to be L, and the spherical or radial node is going to be n minus L minus 1, and total number of nodes is going to be n minus L minus 1 plus L equal to n minus 1. So let us see, for example, let us take 1s. Alright, so in 1s, spherical or radial node, I am going to be writing it as Rn, is going to be 1 minus 0 minus 1, which is going to be 0, and angular node is going to be equal to L, which is also 0. So total nodes is going to be minus 1, n minus 1, which is going to be 0. Alright, because 0 plus 0 is also equal to 0. Similarly for 2s, we get radial nodes, we are going to have 2 minus 0 minus 1, which is going to be 1. Angular node, we are again going to have 0. So total nodes we are going to have 1. Alright, which is n minus 1 as well, and 0 plus 1 as well. Alright, then we have 2p. For 2p radial nodes, we are going to have p is 1, right? So 2 minus 1 minus 1, which is going to be 0. Angular node we are going to have, which is going to be equal to 1, and because it is L, and the total nodes is going to be equal to 1. Alright, so this is what it is. Alright, now let's come out to what I told you about ki jab we were studying about this part. I told you one thing in this part, where the part has gone. Yeah. In the Schrodinger wave equation, I said that there are going to be graphs, and we are going to study some graphs, specific graphs. You need to memorize these graphs. As by memorizing these graphs, as direct questions are sometimes asked that which graph is of what and whatever. So this is 1s graph, this is 2s, and this is 2p. They are different types of graphs. But what you can do, if you are given, sometimes you need to do with options. So if you are given a graph, so you can calculate the number of nodes in it. Is the probability density ever getting 0 in the graph of 1s? No, right? That means number of nodes is going to be equal to 0, which means in the option the number of nodes 0, 1 is going to be true, and you need to take the idea, and then when you get the question in the paper, it's going to be very simple for you. Similarly for 2s, only one node is there. For 2p, only one node is there, right? And there are some equations, like if they give the equation, you can do it like that. Alright, so this is it for the theory part, I think. Yeah, this is it for the theory part. We are done with nodes as well. Now we are going to discuss some questions, important questions related to this topic. I will be focusing more on PYQs right now, because that is what helps you the most, honestly. Okay, so now we move on to some questions that I said that I have handpicked for you guys. Alright, so the first question, here we have the first question, which says that the hydrogen-like species Li2 plus is in a spherically symmetric state S1 with one radial node. Upon absorbing light, the ion undergoes transition to a state S2. The state S2 has one radial node and its energy is equal to the ground energy of the hydrogen atom. The state S1 is. Alright, so these are actually two questions that are paragraph type, like this first question and the second question. This is JEE advanced question. Alright, this is a JEE advanced PYQ. Alright, so for S1, what do we have the information? It's a spherically symmetric state. Alright, it's a spherically symmetric state. That means that it is going to be the S subshell. Alright, S subshell, right? So it's going to be either this or this. This one we can cross out. This is definitely not it. Alright, because spherically, I'm going to write here, spherically symmetric. I told you about the shapes, right? Which means that S subshell. Alright, then we have it's Li2 plus. It has also, here it is written, it has one radial node, and radial node, how do we calculate? N minus L minus 1 equal to 1, and we know that L equal to 0. So N minus 0 minus 1 equal to 1, which is going to be, N is going to be equal to 2. So the S1 is going to be 2S, right? So this one is going to be the correct answer. Alright, now we move on to the second question, which is on the same paragraph, which is based on the same paragraph. It means that it is saying that the orbital angular momentum quantum number of the state S2 is. Now what does this orbital angular momentum quantum number mean? What is this thing? Alright, this means that the L quantum number, the azimuthal quantum number, because here if you see, I taught you guys, I have written here that it is also known as the angular quantum number, and it is also called the orbital angular momentum of electron. It is called the angular quantum number, and it is given orbital angular momentum of electron is given by this quantum number. So it is this one. Alright, but it is asked of the state S2. Alright, we have to tell of the state S2. Now for S2, what it is given, it absorbs light to undergo transition, which means that if it is 2, it is going to go to 3 or 4 or 5 or 6, like this. Alright, it is not going to be less than 2 because it's absorbing light, so it is gaining energy. Alright, so the state S2 has one radial node and its energy is equal to the ground energy of the hydrogen atom. It also has one radial node and the energy is equal to the ground energy of the hydrogen atom. So I think we need to check here. For the ground energy of the hydrogen atom, which means that we have 13.6 Z square by N square, right? So in hydrogen atom, these both are 1. So this means that Z is equal to N. Z is going to be equal to N. Alright, so Z is going to be equal to N, and Z we know already here. Z is lithium, hydrogen, helium, lithium. So N is going to be equal to 3. So N is going to be equal to 3, and now we have one radial node. So for one radial node, we know that N minus L minus 1 equal to 1, which means that 3 minus L minus 1 equal to 1, which means that we have L equal to 1. which means that this is going to be the correct answer. Alright, I hope I am very clear by this point. If there you have any doubt, you can always ask me down in the comments, right? Okay, now in an atom, now the third question. Now this three questions, the last three questions that I'm going to take, these three are of means previous year. All right, they are means previous year. Also, there is one more thing I want to tell, that sometimes it is going to be denoted as this psi 1 2 3, like this. There are going to be three numbers. What does this mean? There is another way to denote this as n l m. So n is going to be the, actually this is wrong, this cannot be, I'm sorry, this cannot be right. All right, let's assume it's going to be 2 1 1. All right, so n is 2, l is, so this simply means that n is 2, l is 1, and m is 1. All right, this is one denotation that I forgot to mention in the above. Okay. Given below are two statements. Statement 1, the orbitals having same energy are called degenerate orbitals. This is right. I explained degenerate orbitals to you. Statement 1 is true. So which means that statement 1 is false while options are going to be wrong. This one is wrong and this one is wrong. Now, it also says in hydrogen atom 3p and 3d orbitals are not degenerate orbitals. This is also wrong, because this statement would be true if this would be for any other atom. But this I explained to you as an exception above, if you remember. This says in hydrogen atom. So in hydrogen atom, these are degenerate orbitals. I explained this to you. Alright. So both statement, statement 1 is true, right? Statement 1 is true because same energy is called degenerate orbital, but statement 2 is false. Alright. So for this option is going to be correct. Now, for this is the last question. This is kind of simple question, but I wanted you to be very clear with this, because you can have some doubts in this. Alright, so the four quantum numbers for the electron in outermost orbital of potassium, atomic number 19, are. So for this question, for these types of questions, we need to write the electronic configuration of potassium. Now this is a very simple thing. They have made our lives easier by telling us that the atomic number is going to be 19. So for atomic number 19, we are going to write 1s2, 2s2, 2p6, 3s2, 3p, wait, let's count. It's 4, 4, 10, 10, 12, 12, 18, and 4s1. Alright? Alright? No, 3d1. 3d. No, 4s1. Sorry. What am I saying? It's 4s1, not 3d1. Sorry. Yeah. Like we can check from this also, right? 1s, 2s, 3s, 4s, 2p, 3p, 4p, 3d, 4d, 4f, right? So in 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, right? This is one. Now we know that the atomic number has gone in this one. Alright, so this is not, actually it's not a difficult question, because we know that there is only one, right? So n is going to be equal to 4 and l is going to be equal to 0. So this is the only correct option, because m is also going to be equal to 0, because there is only one option, and plus half or minus 1 if it depends, and but this option is correct. So I hope this video is clear to you. If you want some other topic you need me to take, or if you have some doubts on this topic, or you have doubts on any other topic in chemistry, you can comment down below. I'll try to answer every question I get. Alright, so thank you very much for watching this video, and I hope to see you soon. If you like this video, please like it, share it with your friends, and subscribe to my channel for more such videos. Thank you.